Okay, welcome to Let's Get to the Marks. We're looking at carboxylic acids. I'm on Physics and Maths Tutor. This is a brilliant website. Yeah, it does have a lot of adverts, but it's an incredible website. You can find tuition on here, but more importantly, it has a totally free bank of questions and answers for all exam boards, for all the science A-levels and maths. So here I'm going to carboxylic acid and derivatives, and we're looking at AQA. And if we come here to these are the recent papers, you can click on that. And let's get into it. Carboxylic acids and derivatives. Which statement about CH3 2 CHCH2 COOH is correct? And we've got four possible answers here, so let's get into it. The first thing I'm going to do is draw the structure of this molecule out. So what we can see here is we've got two methyl groups and then a CH. So let's get those down first. So drawing this first methyl group. So what I'm going to do is I'm going to go through all of these in detail. Obviously, you can do these much quicker, but this is just to give you the extra explanation that's not given to you on the mark schemes, okay? So I'm using the structural formula here to draw out the displayed formula of this molecule. So I'm onto that CH group there that I've circled. Now we've got a CH2, and then we got the carboxylic acid functional group, which is coming off here with an O and an OH. Carbonyl group and the hydroxide group. So in aqueous solution, does it react with magnesium to form carbon dioxide? Well, this is a weak acid, remember? So acid and metal from GCSE, you know, doesn't release carbon dioxide, releases hydrogen. So this is simply a metal in an acid. So let's look at B because A is definitely not the right answer. So let's have a little look at B. It can form hydrogen bonds. Well, in order to form hydrogen bonds, you're going to need one of three different types of bonds, an OH bond, NH bond, or FH bond. Does this have an OH bond? Of course, we've got the alcohol group there on the carboxylic acid functional group. So B is going to be the correct answer, but let me go through the other two now. So C, an optical isomer, this is going to need a carbon with four different groups attached, you know, a chiral carbon. And if we check these, okay, this methyl cup, no, none of these have got four groups attached. This one, four different groups anyway, and the last one only has three groups, so it's definitely not that. IUPAC name, is this 2-methyl butanoic acid? Let's check it out. Okay, well, you can see here the main chain has four carbons in, but actually we don't number it that way. We're going to number with the carboxylic acid functional group as carbon number 1. So this is actually going to be 3-methyl butanoic acid. So this is not the correct name. 2-methyl butanoic acid is not the correct name. This is 3-methyl butanoic acid. So the answer to question 1 is B, and that was a pretty roundabout way to get to that. But hopefully you appreciate the detail and the explanation. Okay, question 2. Which compound is formed when phenylbenzene carboxylate is hydrolyzed under acidic conditions? So we got four answers here, A, B, C, and D. Let's go ahead and draw out phenylbenzene carboxylate so we can work out what the product of its hydrolyzation is. So what the hell is phenylbenzene carboxylate? Well, remember, a phenyl group is simply a benzene ring that's a side chain of another molecule. And then we've actually got a benzene ring here as well with the name benzene. So that means we've got two benzene rings in this molecule. And then we've got carboxylate, and that's like ethanoate, propanoate, the part of an ester that comes from the carboxylic acid. Or if you have a salt of an acid, something like sodium ethanoate, then that's the carboxylate group. So here we go. We've kind of got combine all of these together. So I've got myself a benzene ring. And by the way, I'm going to be doing this in three parts. There's 14 questions in this first carboxylic acids and their derivatives. So I'm going to be doing this in like three parts because there's no way I'm going to be able to do all 14 in one video. So here's the molecule. It's basically got a benzene ring, then the carboxylate group's in the middle there, and then we've got another benzene ring. Okay, neat. Okie dokie, where are we? Right, so we've got this carboxylate group, we've got this benzene, we've got the phenyl. And what you can see is that if you hydrolyze this ester link here in the middle, what's going to happen is you're going to use hydrogen or water to break that down as it's hydrolyzing. So during hydrolysis, we're going to add an OH to the carboxylic acid group, and we're going to add an H to the O there to make an alcohol. So really, when you break up an ester type bond, you're going to form an alcohol and a carboxylic acid. So that means our product A, B, C, or D that it's talking about has to either be an alcohol or an acid. So when we look at this, we can see that A is plausible because A is a benzene group and it has an OH group. It's an alcohol. Okay. The reason I'm crossing it out is because of that carbon. It's not in the right place. And then we look here, and this is an aldehyde. CHO is the functional group. So that's an aldehyde. So that wouldn't get formed under hydrolysis. And then we've got, what is this molecule? Well, this looks like a ketone. Do you notice it's got the carbonyl functional group, the CO, in between the methyl group and the benzene ring? So this looks like some sort of ketone. So again, this wouldn't be formed. So we're really looking for an alcohol or carboxylic acid, which is what you get when you hydrolyze that ester link. And here you go. We've got our carboxylic acid. Recognize that from this drawing up here. And so that means that D is the correct answer. Well done if you got that right. All right, hit the like, subscribe. Let's go. Okay, this is question 3. This question is about esters, including biodiesel. An ester is formed by the reaction of an acid anhydride with, it looks like ethanoic acid here. We'll be given the structural formula. Complete the equation in your answer to show clearly the structure of the ester. Give the IUPAC name of the ester. So we really need to complete this equation, show the two products for 2 marks, and name the ester that's formed. So you've got an acid anhydride here. That's this thing with the double carboxylic acid group. And essentially, if that was a hydrogen atom attached there like that, which I've drawn in black, instead of another carboxylic acid, then you would just form an ester and a water molecule in a condensation reaction. But instead, what we've got going on here is the carboxylic acid, the oxygen on there, is going to join there, and we're going to remove that carboxylic acid. So you really just want to form an ester between one of the carboxylic acids of the acid anhydride and this alcohol. So just make an ester from that carboxylic acid, which is propanoic acid, and the alcohol, and you'll be left with another carboxylic acid. All right, let's show how this works. So yeah, instead of water being released, we've got a carboxylic acid being released. So let's draw this out. We've got CH3, CH2. We're drawing this top carboxylic acid from the acid anhydride. But instead of writing the oxygen here, we're going to attach the oxygen from the alcohol. And this alcohol is ethanol here. So let's attach this. I'll do this in a different color, just so you can see where it's coming from. I've circled the alcohol in green. We're going to attach the alcohol now. Now remember, during this reaction, the hydrogen atom's removed from the OH group. So there we go. We have our ester. So that's going to get us 1 mark for this structure. Now, when naming esters, remember you're going to name the name of the alcohol that formed the ester forms the first part of the ester's name. So this was ethanol, so this is going to be ethyl. And then the second part of the ester's name comes from the carboxylic acid. And so there's 3 carbons in that. So it's going to be propanoic acid and ethanol. What do you make? Ethanol propanoate. And you should know this from GCSE, especially if you did triple. So we've got ethyl propanoate, and we've given the structure. So what is there left to do for the 3rd mark? Well, the 3rd mark here is for working out what the other product is, where I've put my green arrow here. This other product circled in black, this is the other half of the acid anhydride. And of course, I've drawn a little black H on there, and that's exactly what's going to happen. A hydrogen atom is going to join, and we're going to have propanoic acid breaking off as well, which I'm writing here in blue. So we've got the structure for both of our products. They especially wanted the ethyl ethanoate, the ester. We've got our carboxylic acid, and we've named the ester ethyl propanoate. So that's all 3 marks. Well done if you got that right. Remember to pause the video before having a go at these. Okay, part B to this question, let me just make it a bit bigger. This is the dreaded biodiesel. So in a reaction to form biodiesel, 1 mole of vegetable oil reacts with an excess of methanol to form 2 moles of an ester with a molecular formula of C19H34O2 and 1 mole of an ester with a molecular formula of C19H36O2. Draw the structure of the vegetable oil, clearly showing the ester links. You should represent the hydrocarbon chains in the form of CXHY, where X and Y are the actual numbers of carbon and hydrogen atoms. So you should know this reaction off by heart. It's a pretty laborious one to learn and loads of people don't. But essentially, vegetable oil plus 3-methanol or excess methanol is going to give us a glycerol molecule and some methyl esters, normally 3-methyl esters. And they've given us the 3-methyl esters here. We've got one which has the molecular formula C19H36O2 and one which had two which have the formula C19H34O2. Now, those are the molecular formula. Don't get that confused. That's not telling you the nature of the fatty acid chain. That's telling you three separate esters that are formed. So we're going to draw those out over here. So what it doesn't tell you in the question is that these are methyl esters. So they start with a methyl group. That's the H3C group I've written here. Then we've got the ester link followed by the hydrocarbon chain. Okay, so why have I got 2 times methyl group ester link then C17H31? Because we were told there were 2 with H34 and O2. Now the methyl group reduces those hydrogens. So as you can see there, these two together equal 36, the H3 and the 33 from the hydrogen carbon chain. So we've worked out our 3 esters. Why did we do that? That wasn't what the question was asking. Well, we're just starting at this basis. So you also get a glycerol molecule, and you don't really need to work this out. This is this molecule I've just drawn here. 1, 2, 3, propantriol. We don't really need that. That's glycerol. But that would be formed in this reaction. And we don't need this either. This is the 3-methanol molecules, metanols, no, 3-methanol molecules that are going to react with our vegetable oil. Now, here's where we get to the vegetable oil. This is the thing that we're actually being asked to work out in the question. So now we've worked out what our esters look like. I'm circling this bit. These bits are going to be identical over in our vegetable oil. So we're going to have 2 of the first chain and 1 of the second. Okay, so what I'm doing here is drawing out the vegetable oil. So why have I put C17H31? Because that's what was on my ester. And all you're doing is swapping those methyl groups on the front of those esters, those C3H or CH3 groups, for the start of the vegetable oil over here. And you just got to learn the structure of the vegetable oil. The only thing that differs with the different vegetable oils is the size of the carbon hydrogen section, where we've written C17H31. So that's the only thing that's actually going to differ here. The rest of it is always going to be the same. So you can learn the structure of the vegetable oil. You should know the structure of the methyl esters and the glycerol. So this is for the formation of biofuels from vegetable oil. And there we go. This one is slightly longer because this is from the ester, the longer ester with the C19H36O2. So great. Okay, yeah, there's our ester link. We've clearly shown that, which was part of the question. So there you go. That's 2 marks for our vegetable oil, 1 mark for the ester links, 1 mark for the correct carbon hydrogen numbers on those 3 chains. Okay, let's move on. So for part C, it says the compound C19H34O2 is the methyl ester of ZZ or ZZ octadeca 912 dianoic acid. What a serious name that is. Part of the acid structure is shown. Complete the skeletal formula to show the next part of the hydrocarbon chain up to carbon number 14. In your answer, show the Z stereochemistry around both the C double bonds. Now that sounds very intimidating. But the main thing we've got to think about here is we've got some double bonds, and where are they? Well, they're going to be on carbon 9 and 12, and they've handily numbered 7 and 8 for us. And they want us to just do 9, 10, 11, 12, and 14 in a skeletal formula. So we haven't got to draw anything fancy coming off of this. So we're essentially just doing 9, 10, 11, 12, 13, and 14. Now, you wouldn't actually, when you write the skeletal formula, write all these numbers out, but this is just to show you. Now, unfortunately, the structure I've just drawn here is not correct because there's no rotation around the double bond. What we want to do is show that. So we give it a slightly different look. We're going to go like this, and this is going to show that there's no rotation around the double bond, and this is how the cis trans arrives. And this is ZZ, so this is Zusammen or sisters. So they're both going to be on the same side. So let's delete the numbers and we're left with this lovely structure. And if you're wondering how this is cis or ZZ, it's got the hydrogens all would be coming off on this side, okay? And they'd be stuck there because there's no rotation around the double bond. So there you go. That structure there is the correct answer. Okay, give an equation for the complete combustion of the ester C19H34O2. So we just write C19H34O2 plus oxygen forms carbon dioxide and water. Really easy. You just put the 19 from the C there in front there and 34. We need 17 of them to double up on the water. And then we need to work out the oxygen, which you always do last with your combustions. So 9 times 2, we've got 38 oxygens from the carbon dioxide. We've got 17 from the water. 17 and 38 is 55 oxygens left over that we need on the left-hand side. So we come back to the left-hand side and we go, ooh, what's 55 divided by 2? Is it 22.5? No, my brain is rubbish. It's 27. Hold on. 27.5 is 55 divided by 2. So we go, oh, 27.5. But then actually that's incorrect as well, because 27.5 times 2, we forgot about these two that we already have. So actually we only need 53 oxygens to balance the left-hand side. So we do 53 times 2, and that's 26.5. And so 26.5 in front of this O2 plus the 2 in our C19H34O2 makes 55, which we've got on the right hand side. And you can have any multiples of this. So if you don't like dealing in half, some people don't, you can double all of this. Okay, part E. Combustion produces greenhouse gases such as carbon dioxide that cause global warming. Part of the infrared spectrum of carbon dioxide is shown in the diagram. State how the infrared spectrum of carbon dioxide in the diagram above is not what we would expect from the data provided in Table A of the data booklet. Well, if you look in Table A of the data booklet, we would expect carbon dioxide to be around 1,680 to 1,750. That's where the COO bond from the carbon dioxide should be. What we actually find here is we've got an absorption at 2,300 and 2,350, sort of around that range is where the absorption is. We would expect it not to be there. On the data book, it should be 1,680, but there we go. Okay, and then the next part of this question is, so we would expect blah, 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 blah. Yeah, moving on. Explain how carbon dioxide causes global warming. So loads of answers you can give here, but essentially the bond absorbs the energy at the 200, 2000, whatever we quoted there. Yeah, 2300 to 2350. That's the wavelength of the energy. I've written just energy, but that's stupid of me. That's the wavelength of the energy that it absorbs, the CO bond in the carbon dioxide, which means that less energy is released to the atmosphere or emitted. You can say more energy is trapped or heat energy is trapped in the atmosphere. Cool. Let's get down to the final question for this this video on carboxylic acids. I'm going to do the rest of these questions in my next video. Which compound is formed by acid hydrolysis? Phenyl, methyl, ethanoate. Well, if we break down that word phenyl, we've already talked about the phenyl means it's a benzene ring that's a side chain. We've then got a methyl group attached and the ethanoate. So this is like, yeah, whatever. Uh, there we go. There's the structure. So remember that this has come from a carboxylic acid and an alcohol, so likely to be ethanoic acid and then the alcohol with the benzene ring. So which compound would be formed when we split that? So go through A, B, C, D, see if you can work it out. Here's what phenyl methyl ethanoate would look like. And now go through, separate it into a carboxylic acid. You can do that with the carbonyl group, separate it into the alcohol. The O in the ester link always comes from the alcohol. So I'm circling around the benzene ring, the CHH and the O here, which come from the alcohol. And this second circle I'm making is the carboxylic acid. So now work out which one of these products could have possibly come from either half of that phenyl. So if we look first at A, we can see we've got a benzene group, C6H5, that stands for benzene. Then we've got CH2, then OH. So that looks pretty good. If we draw that out here, we've got the benzene. Coming off of it, we've got CH2, which is just what my diagram has above. And then we've got OH. So that's the correct answer. But let me go through the others for you. You've got one here. This is an aldehyde. So benzene ring with a CHO on it. Now we've got a ketone, we've got a benzene ring with a carbonyl group in between the methyl group and the benzene ring. So that's not going to form when you break up a phenyl methyl ethanoate or a phenyl ester or whatever we want to call it. And then we've got a carboxylic acid down here. Now, technically, the carboxylic acid could have been made, but you can see from the diagram up above, the carboxylic acid is not attached directly to the ring, and this one would be attached directly to the ring. So this is not the correct answer. D is not correct because it's not directly attached to the ring. So there we go. Hope that was helpful, and that's the end of this little session on carboxylic acids and derivatives from the Physics and Maths Tutor site. I'll be dropping another video for part 2 of this and part 3 within the next week. So keep tuned, subscribe, let's get to the mark.
You're still here? It's over.